Hello students, we have seen the equation of motion for a single degree of freedom system. Okay, and that equation was something like this: mx double dot plus kx equal to 0. Okay, now this equation is referred to as second order ordinary differential equation. Okay, now if you see in this equation, which is unknown in it, unknown is x. X is how exactly the displacement is varying with time. Okay, so x is function of time. Okay, time is independent and x is a dependent quantity. Okay, and that x how exactly depends on time, that we are unaware of. Okay, so if we have on x-axis time and y-axis is that of x, so we don't know what is this f of x. Okay, so as of now we are unaware of this, sorry, f of t, that we are unaware of. So how exactly x is varying with respect to time is something that we are not aware of. So this is what we are going to find out. However, what we know is that there is certain relationship between this function and its second derivative. Okay, second derivative is this x double dot, which is acceleration. So we have enforced relationship between second derivative of that unknown function and that unknown function itself, and the highest derivative which is appearing in this relationship is second. That's why it is called as a second order differential equation. This is a differential equation which is relating unknown function with its derivative. Okay, and the derivative which is appearing in this equation, highest order of that derivative is second. That's why it is a second order differential equation. Now there is one more word which is over here, which is ordinary. O stands for ordinary over here. So what is the ordinary ordinary in this? The ordinary word refers to how many number of independent variables are there. Okay, so this unknown, which is x, depends on how many number of variables. It depends on only one variable. So when you have only one independent variable, that time that differential equation is called as ordinary differential equation. Since time is the only controlling variable, so that's why this is ordinary differential equation. Okay, had it been dependent on some other, let's say, spatial coordinate, then that also would have appeared over here, and then the equation would have been partial differential equation. But in this particular case, our equation is ordinary differential equation and its order is second order. So this is second order ordinary differential equation. You might have already studied this. Okay, so you can think of it as kind of a recap of whatever that you have studied before. Okay, so now in order to, the question is whether are we done with posing the problem completely. The answer is no. This is not the only thing that we should have in order to pose the problem completely. So what else is required? Something else is required, which we will be calling as initial conditions. Okay, so there are two more conditions which we'll have to specify. Okay, so two conditions in all. So why two conditions? Because equation is second order. Okay, so there are going to be, so when we are going to solve this equation, there will be two unknown quantities which will constants which are going to appear into that, and those two unknown constants need to be determined, and in order to determine those constants and in order to get the unique solution, we need two conditions. Okay, those conditions are specified at the beginning. Okay, so at the start. Okay, so whenever you will be starting, so what happens at that moment? Okay, so you will be specifying two conditions, and that's why it is called as initial one. So it is at the start two conditions are specified, that's why it is initial problem. Okay, so this typical vibration problem is second order initial condition problem. Okay, now since the equation, as I just now told you, that equation has got highest order derivative which is second order, so you are going to need two conditions, and those two conditions will be on x and x dot. Okay, so on the primary variable, which is x, and one more derivative of it, so which is one order lesser than what appears in the differential equation. In the differential equation, the highest order derivative which is appearing is x double dot. So you will need to specify conditions, initial conditions on those many derivatives which are one less than this. Okay, so which is x dot. So you will have to specify x and x dot. So once you specify x and x dot at the beginning along with this equation, then your problem is completely defined. Okay, so at time t equal to t0, you need to tell what is x and what is x dot. Okay, so it's like, so let me draw the system that we are talking about. Okay, so it's like specifying how much initial displacement you are giving to this mass. Are you bringing this mass and pulling it over here? Okay, and while you leave this mass, okay, when you let this mass start oscillatory motion, how much is this x and is there any x dot? So if there is any x dot, how much is that x dot? So either you can give x as 0 and some x dot, okay, or you can give it some displacement to start with, okay, some non-zero displacement and 0 initial velocity. That is, the mass is at rest, okay, at the beginning, at the start, okay, and you leave it and then it performs oscillatory motion. When you have x dot specified, assume as if you are hammering over here, okay, just giving some impact at this location, okay, right at the beginning, okay, which is in this mean position, and then the mass will carry out the oscillatory motion, okay, or you can have combination of both of them. Okay, so with these two conditions, with x specified at x equal to t at time t equal to t0 and x dot specified again at time t equal to t0. Okay, so what is this and what is this? So these are the two conditions which you will have to specify. So two initial conditions along with this differential equation. Okay, so this is the complete problem. Okay, so now you have defined the problem completely. So with this much of initial displacement and with this much of initial velocity, if this is going to be the relationship between acceleration and the displacement, now you tell me how exactly displacement is going to change with respect to time. Okay, so how is this going to happen? Okay, so what will be the nature of this solution? Okay, so this is the problem. Okay, now let's try to see how exactly the solution can be arrived at.